Okay. So far what we have seen an example of a linear regression where we learned how to clean the data. Okay. So cleaning required us to do missing value, replacing the missing value, handling the categorical data, then dividing into train set and test set, and then we did normalization, right? These were the things that we did as part of our pre-processing, data pre-processing. Then we had a data set with just one X value, one independent variable, okay, which was ours, and dependent variable marks. So we ran linear regression model, okay. And so how did we run linear regression? We called linear model from sklearn, which has linear regression class. So we created object of linear regression and we did regressor.fit. This is how you train the algorithm. So when training is done, then we actually displayed. We saw that we are talking about linear regression where the regression is a straight line, right? Regression is done along the straight line. The equation of that straight line is given by is got after we perform the fit, right? So we have this coefficient and intercept. Okay. Then what we did, the test data that we had hidden from the model. So we used test data to make prediction. So ypred, we said, okay, regressor now predict it for X test. So X test is only the X column, right? The independent columns, not the Y value. So regressor will predict and it will put it in ypred. Now, okay, we want to compare how well it has predicted, right? So you can compare the value. And this is what we did in the last session. It helped us to predict the value. Okay, then we are comparing the actual value which we had in y test versus the ypred that we calculated here. And you can see the output here. Now, so this is how well, we have calculated or we predicted the value. Okay, so you can actually calculate for each of these things, isn't it? Now we need to understand, okay, how well the model has performed. Okay, now again, this is very similar to the way we could calculate standard deviation or variance. Okay, so what I'll do, okay, manually I'll show you how we can compare these values, and then we will see the metric that we use from sklearn, scikit-learn to get the same values. So I'm going to start my Excel. Okay, I'll take you to the Excel sheet just a second. Okay, now you should be able to see my, not yet, wait. When I start something, my system becomes slow, any application. Just give me a second. Okay, now you should be able to see the Excel, right? So here I put a y test, the actual value, or we'll call it as actual. Okay, and this is your predicted value, right? So let me copy it quickly from here. Okay, so you have 46, 94, 98, 46, 45, 46. And here you have 49.3, 92.8, 98.8, 52.3, 43.3, 51.6. Okay. Now, how do we know how well this has done? So first thing you have to do is find the difference between them. Okay. So I'll say difference. Difference would be either you do actual minus predicted or you do predicted minus actual. So I want to compare from actual, right? How we have done with respect to actual. So you say actual minus predicted. Okay. So here you got wrong by 3.3. You predicted more than what is actually it was. So minus sign and 3 is the difference, 3.3. Okay. So you can calculate for all of these. Now this is for each row, right? It is for each row. Okay. So this is the difference, okay, or the error, right? So in statistics, in mathematics, we call them as difference. But in machine learning, this is our error, isn't it? Correct? Because this is the error. Okay, you expect 49, but you expect 46, but you got 49. That's an error, right? Okay, you nothing more, nothing less, right? You want 46. Actual value was 46. This is what you expect the model to give you, but you got something different, right? So that's an error, right? So this is an error. Now, again, I just said same thing if you do in statistics, it's called difference. Mathematics, we call them difference, right? But here we call this as error, okay? Now, this is the error for each, right? Now, I want to find error value for the entire model, right? I want to find the error for the entire model. So what I'll do, I will add them together, okay, and find the average. Okay, I mean, I'll find them average. So I'll add them together and divide by n, but directly I'll say average. Okay. So what is this called? Average error. In mathematics, you call them as average difference. In our machine learning, we call this as average error, right? This is the average error. So minus 2.1 is the average error. Is this right? The concept is right here? No. See here you have some plus values and some minus values, right? So this minus and plus, they're canceling each other, isn't it? And what we want them is that if it is error, it is error. Whether if I make, the first time I predict 5 values higher, and second time I predict 5 values lower, average will make it 0, isn't it? It'll say, oh, perfect, your model is perfect, average error is 0. But that's not right. Okay, minus 5 is also error, plus 5 is also error, right? So what we need to do is we need to do something so that error gets added together, not cancelled here, just like here. So for this, okay, how do we make sure that minus and plus numbers are added together? So before you find average, you find the absolute value of these values. Okay, you find the absolute value. So what we'll do, we'll say here, okay, average is also called as your mean error, isn't it? Mean. So we'll replace average with mean. So this is your mean error. Now we will find absolute error. Absolute error, okay, we need to make negative value positive, positive value will become positive. Okay, so this is how you will calculate, and now you calculate the error. Okay, so error is 3.1. This is somewhat better than this one. So we call this as mean, okay, mean average, mean absolute error, MAE, or in statistics, we call this as MAD, mean absolute difference, mean absolute difference. And here we'll say mean absolute error. This is your mean error, and this is mean absolute error, isn't it? So you found error, then we did absolute. So when you see something like mean absolute error, that means first you have done error, then you have done absolute, then you have done mean. So error, absolute, mean. So mean, absolute, error. Okay, this is what we have done, right? So this is one metric that we look at. Then there's another way to make a negative number positive. What is that metric?
Squaring of.
Squaring the negative numbers, yes. So I'll do what is called as squared error. Okay. In statistics, we call it as squared difference. In machine learning, we'll call it as squared error. So you will say this number into this number. Right? Now you find the average of this. What shall we call this? What did we get here? What shall we call this? Louder.
Mean squared error.
Mean squared error. Yes. Okay. And what do we call this in statistics?
Mean squared difference.
Variance.
Variance.
Variance is mean squared difference. Okay, this is what we say variance. Variance is your mean squared difference. MSD. MSD in statistics we same as variance. This is called variance. Okay. In our language, in our machine learning language, we'll call it as mean squared error. So mean absolute error, mean squared error. But mean absolute error is not generally considered as a good metric. Why? Because we started with x and we became x square. So we started with error and it became squared error, which is not right, correct? The metric should be in similar range. You start with apple and you say, okay, answer is 10 oranges, correct? That's not right, right? We have to bring it down to same level. Since we have done square here, okay, we will do square root of this value, okay? So you find square root of this, SQRT of this. Okay, we need to perform square root of this value. Okay. So now what do we call this value?
Root mean squared.
Root mean squared error. Okay. So yes, this is your root mean squared error, and this is the most important metric. Second important is MAE. Third is mean squared. Mean squared error is nothing but square of RMSE, or in statistics, what we call this as standard deviation. This is your standard deviation in statistics. This is what we say, okay, in
Statistics.
that is standard deviation. This is why we do standard deviation as square root of variance. Okay, we do square root of variance because variance is square. We started with error and we started with difference and became difference square.
Yes.
Yes, you have to bring it down to the same level. So you have to do square root. So that's why we know so in statistics also variance is not used, right? We use mostly standard deviation. Okay, so it's called root mean squared error, RMSE. Okay, so RMSE is the most important metric. Okay, you need to remember to calculate the error between. Okay, or if you have to know how well your model has done. Okay. Okay. So this is one important metric, and second important metric is called R square. Okay. Second important metric is called R square. We need to calculate R square. What is R square? R square compares your value, okay, with your prediction, okay, what you predicted using the model versus if you had not run the model and used average instead. Okay, if you had not predicted the model and used average instead, how it would have looked like? How well have you predicted the model with respect to average? So the other day we told you, right? If you do not know regression, if we have no idea what we generally do, we take the average of the entire data set, right? Example I said, I gave you, like if you want to predict your cousin's mark, you'll say, okay, on average, people in this school get 70%, so my cousin will get 70%. So you're talking about the average of the class, not specific average, looking at the individual's performance. We are not personalizing it, but with regression, you can personalize it, right? So next important metric is called R square. It's called R square. Now this R square, I just said, compares your, okay, metric with respect to squared metrics, okay? Sorry, average metrics. So if you had not taken the regression line, instead taken the average line, okay? So let me quickly take you to paint here. Okay, so let's say you have this XY plane. You have this XY plane and you had this values here. So you decided to use linear regression and you got a linear regression, something like this. Now, I don't want to use linear regression. If I, okay, or rather, if I had used average with our entire data set would have been somewhere here, right? If I had taken average from, let's say this is 10 to 90, okay? So average probably would have been about 45 or something, okay? Or 50 or 60, whatever, right? So I would have drawn a line at 60, let's say if 60 is the average. So now we say how well this red line or regression line has performed better than this average line, blue line. Okay, so you find that error between this, this, okay? So you add this error and then you find the error between blue line and this. So blue line, let me use green color. So blue line and this. Which error will be more? The distance between blue line to the points or red line to the point, to the points. Which will have higher error? Hmm?
Green line will have higher error.
Of course. Why are you thinking? I don't even understand. If green line, if the red line had error, then why would you learn even regression?
Oh.
Use your brain, guys. Come on, we are in the last phase, right?
Fine.
So yes, red line will have less error. That's why we are doing regression. If we had, if average line will give you less error, then why even learn regression? Why even spend time learning something, which is not helpful to us? We want to predict with better accuracy. And you can clearly see, right? See, green line is going so far, right? Red line, obviously points will be closer to red line. That's what the meaning of regression line is. The best fit line, the line that will have least error. You cannot have any other line which will have least error. Any other line, if you take, even if you take something closer to this also, okay, if you take something closer to red line also, this green line will have higher error than the red line. Obviously,
Yes. Yes.
because the definition itself says that red line is the line with the least error. If red line is the line with the least error, any other line will have higher error, yes or no? Okay,
Yes.
so we are talking about R square metric, and R square is written as, okay, formula I'll tell you, formula you can actually see, but generally what R square means. So we represent it R square, okay, is equal to, okay, your sum of, okay, it says 1 minus, okay, 1 minus sum of your error with respect to regression line. So I can say error, okay, error is total error, okay, sum. Error with respect to regression line divided by error with respect to average line. Formula is something else. Formula is, n into sigma of xy. Okay. So the notes which I'll share will have the formula. Okay. So no worries. N into sigma of xy minus sigma of x into sigma of y. You add x, you add y. Okay. What is x and y here? Okay. Divided by square root of difference between the points. So, you have n into sigma x square minus sigma x whole square. Okay, this is 1, and then you multiply this with same thing other side. Okay, n sigma y square minus sigma y whole square. Okay, that's the formula. What is x and y here?
X will be
Guess? I told you the actual meaning. This is the meaning, okay? 1 minus error. And this is how we actually calculate.
x, y, x.
So you have the points, right? Okay, if
yes.
you look at this point, this is your x value. This is your y
Y value.
value, right? So when I say sigma xy, that means it is like x1 into y1. Sigma means plus, summation, plus x2 into y2, plus x3 into y3, plus x4 into y4, plus x5 into y5, plus, right? That's what it means, isn't it? So you are calculating this value, okay, x and y value from the given, yeah, from the given formula, and you get R square. But we don't have to remember the formula for our work because all these metric, okay, are directly given by a library called as metric, okay, metric. Now, before we move to our program, tell me here, what could be the maximum value of R square and what could be the minimum value of R square? When do you say, R square value is maximum? When the error on red line is 0. Regression line is 0, right? When, your prediction, your model has predicted 100% accuracy, correct? That's when we say R square is best, correct? If your model has predicted with 100% accuracy, you will say your model has done very well, right? You can't have a model better than 100%, isn't it? Okay, no error. RMSE is 0. See, RMSE, as the value is higher, you say error is higher. And your RMSE is lower, you say, accuracy is better. Your model is doing better job. So if you have to compare two model, You compare the RMSE, and the one with the lower RMSE is a better model. With me?
Yes.
Now in R square, okay, we generally look at in a better, higher the R square, better it is. But what could be the highest value of R square? See, highest value of R square is when error on the red line or regression line is 0. And your regression line has predicted the values with 100% accuracy. Okay, so 0 by anything is 0 only.
Yes.
1 minus 0 will be 1 only.
1.
So R square can take a maximum value of 1. What is minimum value that it can take practically? And we'll talk about theoretically also. Practically, okay, what could be the value of lowest value? Okay, lowest value is when your average line is same as the regression line. Okay, your regression line is same as the average line. Okay, your regression line falls on the average line. Okay, so your regression, so error, because it's both same now, right?
Yes.
So error on the numerator and denominator will be same. So it is 1.
1.
1
0.
minus 1 is 0. Okay, so minimum value that R can take is 0. This is called as worst model. Okay, and this is the best possible model. Okay, this is the best. You can't have a model better than 1, and you can't have a model lower than 0. Okay, now why did you say practically or theoretically? Theoretically, this can have a higher error. Okay, theoretically, this can have a higher error. So let's say this error has 6, and this error is only 3. Average error is only 3, and this is 6. So 6 by 3 will give you 2. 1 minus 2 will be
Minus 1.
negative, minus, right? So R square can go to negative also.
Negative. Yes.
Okay, theoretically. But why can't you, when I say practically, why it can't be, negative practically?
Because
Why can't it be negative?
we are squaring it, right?
No, where are we squaring? You see on the top, okay, numerator is not, okay, squaring. See, it can be negative theoretically when numerator is error, regression line is greater than error on average line. But practically it can't be, because what did we say? We said that the line with the least error is regression line.
Yes.
So this cannot be more than this. In the worst case, they can be same. See, by definition, if average line is giving you better result than the regression line, if average line is giving you better accuracy than average line, regression line, then this becomes the regression line, isn't it?
Yes. Yes. Yes.
By definition itself, what we said, the line that gives us the best result, least error is regression
Best
line.
result.
So if average line is giving you least result, least error, then average line is
Yes.
regression line. Now the meaning, the definition itself changes. So you can never have numerator greater than denominator. No. Yes or no? Error, numerator cannot be more than the error in the
Yes.
denominator. Yes or no? Right? So that's why we say that R square value cannot be practically be less than 1. Okay. But if you have done created mess, it can be negative also. Okay. So two important metric we use to evaluate the performance of a model. What is that called? That is called as R square and RMSE. R square and RMSE are the two important model or two important metric that we use. But we also have a metric like mean squared error, um, mean error itself, right? Okay. Now let's go back to our program and learn how to calculate these values. Okay. So I'm switching to PyCharm here. Okay. So analyzing the output. Okay. How do you analyze the output? So I'm going to use something called as metric. So I'm going to say from sklearn import metric. metrics. Okay, this has all the metrics that we need. So if you want to talk about, I see there are many. Okay, if you can remember all, I mean you can't remember all. There are too many, but okay, try to remember these two things at least: RMSE and R square. Okay, okay. Interesting thing is there is no way to calculate RMSE. There is no RMSE thing in metric. What metric has is mean. Okay, so mean squared error, right? So you say matrix dot mean. Now see, these are the values: mean, squared error, mean absolute error, right? If you wanted to calculate mean absolute error, you can calculate as mean absolute error, mean squared error. Okay, so I'm going to say mean squared error, and it takes first y true, that is actual value, and y pred, the predicted value. Okay, so error, and I'll say y true equal to y test, right? This is our test value. And then y pred equal to our y pred value, right? Okay. So this is going to give us MSE, right? And I'm interested in root mean squared error. Okay, so print root mean squared error. So I'll say RM math dot, or I can directly say MSE into 0.5, right? So MSE to the power of, double star is power of. So MSE to the power of 1/2 or 0.5 will give us square root.
Hmm.
This should be 3.8. This is what we had calculated in Excel, 3.8. Let's see, we get 3.8 or not here. You got 3.8, right? This is what we had calculated in Excel also, isn't it? So root mean squared error is square root of MSE. If you want to calculate mean absolute error is matrix dot mean absolute error. Okay, and we need to give same value here. So I'm going to copy and paste it here, and then you print. So what did we calculate as mean absolute error? Do you remember? 3.1, right? Mean absolute error. So MAE, directly MAE. We don't have to do any calculation. Okay, and then you have R squared value, right? So let it calculate. Meanwhile, we'll print R squared. So see 3.1. This is what we had calculated in Excel also. R squared. Okay, mean absolute error and R squared. These are two important metrics that you have to remember. Okay, then you have mean, explained variance. You have mean squared log error. You have mean, median absolute error, right? You also have median absolute error. Instead of calculating mean, you can also calculate median. So median absolute error, all those metrics are there, but we will look at only these two. Okay, so now I'll say print R square is comma matrix dot, okay, R2 score, R square score. Okay, and this will need your this will need your values. What values we gave? Y true and Y pred. If you're giving in same order, then you don't have to say Y true. Okay, directly say Y test and Y pred. Because first two input were, so again, if you have to remember your functions classes. Okay, so this is like keyword arguments. Okay, keyword. So you're calling the variable that is being used in the function definition. And this is like your first type, required arguments. Okay, so for this experiment, you get R square as somewhere around 0.9, I guess. Yes, you see, 0.97. So this is how you analyze your model. Okay, so you clean the data, you run the model, and you analyze the model. Okay, this is about regression algorithm. Now, if you're talking about classification, of course, till here it will be same. Here it will be different, right? Because there you won't get numbers. So we can't calculate difference error. We can't calculate error, right? Or the difference, right? We have to use some other concept there. But we'll see when we go there. We still have long way to go there. We still have a lot of things to discuss in regression before we go there. Okay. So this is how you analyze the data. Right? Yes?
Yes.
We
Yes.
also have another, so this is just one model, right? We have to do different models. So this model, we said it's simple. Why it's called simple?
We have only one X.
Yes, we have only one input variable. Okay, that's why we say simple. Okay, life is not simple, right? So we will
Yes.
see how to have multiple input values. Okay, but before that, okay, there's one important concept that we have to understand. Okay, the concept is called bias versus variance. Okay, let's understand this bias versus variance. Now, let me take an example here. Let's take a boy, okay, or a girl, doesn't matter, okay. Now, this guy, okay, gets 99% in the exam, but miserably fails in the interview, in the, say, job interview. Okay, the situation, I'm just trying to make you understand. Now, what do you get from this feeling? What does it tell you?
We couldn't perform well in explaining things, giving interview.
That's what I'm saying. Fails, did not perform. What does that it tell you about the guy's preparation? Okay. So for a second, let's go back to our paint again. Okay, so there are 4 possibilities, right? So what are the 4 possibilities? You have possibilities like, okay, this is at college level. And this is like, say, job level. So you can perform, and let's say this is bad, worst, and best. Worst and best. Okay. Possibilities. Okay, this is where the student performs bad in college. Okay, performs bad in college and bad in job. This is where student performs best at college, right? But this is
Worst at
situation
job.
1, performs worst in both the cases. Here, you perform best in college, the example which I gave you, right? 99% at college, but let's say 2% at job. Worst. Situation 2. Situation 3, let's say it is best in both the cases. Does very well in the exam, does very well in the job interview. This is where this has done worst in the college, okay, and perform best at job. So 4 possibilities, right? Now, what each of these possibilities tell you? This possibility tells you that, this guy is probably not fit, right? Probably, should do something else, not do this work. Okay. This is something which is probably impossible, not possible. Okay. If you are good, you will do good in college also, isn't it? Why will you perform bad in college? Okay. So this kind of situation probably may not occur. thing is here, what do we do? This is the best. Blindly, you can hire that student, right? 99% does well in the interview, you can hire this student direct blindly. Here, okay, why is that able to perform best in college and not so good at job? Okay, maybe, this fellow has got the question paper, right? Or somebody, would have
Yes.
guessed the question or something, right? So now let's take it to our model. College is like training. College is like training, and job is like your test data. And performance is like your R square or RMSE, whatever you say, right? Now, what I'm saying here, I'm saying your RMSE or RMSE is low or R square is highest in both training and test. In both training and test. Now, you tell me in the current model that we have developed, okay, we did RMSE and R square on the test data, isn't it? We are testing
Yes.
the model. That's like, job interview, testing the model. Okay. So we calculated RMSE and R square on the test data. Okay. RMSE and R square on the test data we calculate. We need to calculate same thing on the training data also. So training data is going to be your college kind of situation, and test data is going to be a job kind of situation. You're testing the model. Okay. So if your model is performing very good on both training and test, okay, so then you will not have any question. You will take that. Now let's say there are 10 students performing very well, right? Then that's a different way we'll measure. But first, okay, if they are performing well on both, you have no questions to ask. If you are performing worst on both, you have no questions to ask because you want to reject it anyway. No questions. Questions will come when you have this kind of situation, right? Here, no questions, okay? You can blindly delete it. Here, no question. You can blindly accept it, okay? Not practically, this will not occur. This should not occur, okay? The data which I'm giving you for the training, you're performing worst on that, but data which I'm testing you on, you're doing good. Sometimes it doesn't seem to be right? Though it can happen, right? But generally, we ignore. We don't want to get into that kind of situation. If you see something like this, that means you have to rechange the strategy. You have to change the data or something is wrong. Maybe you're using wrong model, right? You should be using different model or something like that. So this also we reject, and this also we reject, right? Okay, because okay. So this is what we say we accept. We accept, okay? Now we're talking about variance and bias. Okay? Bias. Variance is error, right? And bias is that you are being biased towards the data set. You're going by the data set. Variance is the genuine error. Yes?
Yes.
So, bias is, okay, you're going with the data set and you are not able to perform well at college. When you perform worst with the training data, it's called biased. If your error with the training data is high, we say high bias. See, bias and variance both are error. Bias and variance both are error. Okay, bias and variance both are error. Both has to be low, right? If both are low, you are in third, third box here. This is where, when we say bias is also low, the bias is the student has performed well in college. And variance is also low because variance is the error at the test data, okay, at the job level. Remember this way. So bias is the error with the training data. Variance is the error with the test data. Variance is the error with the test data. Bias is the variance, or sorry, a difference of with the training data. So in this case, you tell me with respect to bias and variance, which will be high and which will be low? In third box.
Third box.
Third box, yes. Which will be high, which will be low?
Training will be low.
Okay. Training, there is nothing called training. We have bias and variance.
Okay. So bias will be low.
Bias will be low. Okay. And what about variance?
Variance will be high because he's unable
Variance
to
will also
perform.
be low. This is your best performing model, best in college, best in job. So it is
No,
bias will be low
okay,
and
okay,
variance
okay.
will also be low.
Okay, I was seeing that second. Okay, okay.
No, I'm
Yes.
telling you third,
Yes,
right?
yes, correct.
Bias
Correct.
will be low and variance will be low. Now in first
Yeah.
case,
Yes, sir.
tell me one first case.
First case, both will be low.
Both will be low, right?
Yes.
Bias will, both will be lower. Both will be high.
Worst.
Yes, bias is error. Error high means worst. Error
Okay.
is what? Okay, error high means worst model. Error low means good model.
Okay.
So
Okay.
here, because it is worst model, your bias will also be high
No.
and your variance will also be
Yes, yes.
high.
Yes.
High variance, high bias. Now second
Yes.
case,
Both will be high.
think and tell me.
In second case, bias will
Bias,
be low.
training. Bias is best performing.
Yes.
So
It will be
bias
low.
will be low.
Low.
Variance will be worst,
Variance will be
high.
high. Yes.
So bias will be low and variance will be high.
Yes.
In this situation, your bias will be high and your variance will be low.
Yes.
Okay. Okay. So these are the
Yes,
four
sir.
situations. Your high bias, high variance, low bias, low variance, high bias, low variance, high variance, low bias. These are the four situations that you will come across. Okay. And I told you bias high and variance low is very rare. You should not come across this. You will come across these three. Okay. And these three, okay, will tell you, okay, what we need to do. Now, see, I am not using a word like, it should be more than 70%, less than 60%. No, I'm using low and high. Your low and high will vary based on the data you are dealing with. In some case, 80% accuracy may be bad. In some case, 80% accuracy may be very high. Okay. So it depends upon the data. Okay. Depends upon the situation. Okay. Things like I told you before, I don't know, if you're predicting, let's say, grocery sale, atta sale, rice sale, that doesn't fluctuate with GDP, right? Doesn't fluctuate with, increase in, the amount of rice that you will eat doesn't depend upon your salary, isn't it? Oh, I got a bonus, let me eat extra rice today, right?
Yes.
No, right? So these products have a stable consumption and it is easy to predict. Okay. But let's say prediction of, buying car. Yes, you got a bonus, you can buy a car. Okay. So that is dependent on your various factors and it is difficult to predict. Comparatively, it is easier to predict the rice consumption against car consumption. If you're trying to predict number of cars, that will be manufactured in next year, next quarter, next month. Okay, there 90% is very good accuracy. Okay, but if you're talking about how much rice will be consumed next month, 90% will be worst accuracy, right? Because there you expect 98, 99% accuracy. So the low and high value will fluctuate between your based on your problem statement, isn't it? So this is example of how you first you evaluate the model and then you check if your evaluation is right or not. Are you evaluating correctly or not? Okay, should you blindly accept the output? If this is the case, then yes, you should blindly accept the result. Otherwise, you should not. Yes? Okay. So along with finding the
Yes.
RMSE value, R-square value, you also need to find the bias and the variance. How do you calculate the bias and the variance? Okay, let's go back. What did I say? What is bias? Bias is the accuracy on
Parallel training set.
bias is the accuracy of training set, isn't it?
Training set. Yes.
Here we did on test set, correct?
Yes.
We did on test set. So this is bias or variance.
Variance.
This is variance, exactly. This is your variance, okay? This is your variance. Now, how do you calculate bias? So to calculate bias, we need to use training data, right? Bias is based on training data. So what I'll do, I will do YPRED only. Okay, I will do YPRED. Okay, but I'll put YPRED training data. Okay, and this you're predicting on training data. See, same set on which you train the model, and on same thing I am predicting. So it's like I gave you 10 examples to solve, and on the same 10 example, I'm testing your accuracy. Okay. So the data on which I trained you, on same data I'm taking in the test. And if you perform very well, and if you don't perform well in the test, that means you have by-hearted, mugged up, isn't it? So I'm testing you on training. Okay. You want person who is thinking. We want model which is thinking. We don't want model which is mugging up the answers.
Yes.
Right? So a model which is performing very good on training data, which has a very low bias, very, very low bias, and medium, very low bias, but medium variance is okay. We don't prefer that, but we'll prefer a model which has medium on both bias and variance. Why? Okay, because that model is thinking, that model has not mugged up and given the answer. So this is called
Okay.
calculating your bias. I'm going to say YPRED training. Now we can calculate our, MSE, and we'll delete MAE. Okay, so root means squared, bias. Bias is MSE on
Training.
YPRED training. Okay, this is true value, right? YPRED training, and this is your Y train. Y train is the actual value, right? For training data. Y train. This is your bias. This is your bias. Mean absolute error, we don't want, we'll delete it. Okay, so we calculate RMSE and we calculated R-square. Let's compare. Okay. So this is how you calculate bias and variance. Bias is based on your accuracy, based on your training data. And variance is based on, so now you see here, okay, this data is funny. It has performed very well on, this is the fourth case, which we generally don't expect. Right? So here you see RMSE on variance is 3.8. Okay, on test data. On training data, it is 4.6.
4.62.
Hey, so this is higher. We expect bias to be lower. That means probably you're not using the right model. Or in this case, why it's happening is because we are not using we have very few rows. Okay. Okay. But at least the model is thinking.
Yes.
Okay. Okay. So this is how you calculate your variance and bias. Now let's see what happens. Again, I'm going back to Paint. Okay. Let's say you have a graph like this, X, Y, and what I'm going to do is I'm going to have, this is, let's say, number of rows. See, one more factor is the number of rows, okay, or data, amount of data, okay, and this is like accuracy, okay. Now you decide whether it is accuracy or error. Let's say I put this as accuracy, or let's talking about error, right? Let's talk about error only, right? We're talking about RMSE, so RMSE is error, right? So this is, let's say, error. Error, this is 100%. That means 0% accuracy, and this is 0% error, that is 100% accuracy. Okay. Initially, what happens when you have less data set like this, your error will be high. Both your bias and variance, both will be high. So let's talk about bias first. Bias is training data. Okay. So your training data, error will be high. And as you perform, okay, more and more analysis on it, as you perform, okay, you give more data, okay, your error will start decreasing. Okay, this is what you will notice when you have. So this could be because of providing more data. This could be because that you are fine tuning more. Okay, so in linear regression we didn't have any parameters, but next algorithm I'm going to talk about will have parameters. Okay, so we'll see that. And actually, the next example only I'll show you this. So what is happening here? Your training error or bias or training error. Train error, we also call as training error, train error. Train error will keep on decreasing. Will keep on decreasing if you add more and more data, as you change the parameter tuning and things like that. This will start decreasing, okay, as it'll keep on decreasing. But your test error, so generally error will be higher, right? So test error will be higher here. Let's say, this is where you start with variance. Variance will also start decreasing. Okay, will also start decreasing. After a certain point, this will start increasing. This is where your students have started mugging up, right? So as you give more and more, let's see, if I give you only one topic, if I teach you only one topic and I take you test, okay, you will do bad on both training and test, right? If I give you 22 topics, you'll do worst on both. Okay, so it's not your mistake. You have not got enough training, right? Okay, so see, this is the point where it starts increasing, right? This is the point where you have minimum, okay, both minimum train error and minimum test error. Okay, this is called the region of best fit. Okay, beyond this, what is happening? Okay, students are mugging up. So when you start mugging up, your class performance will become better. You'll get 90%, 99%, 100%. But when you go to job, you will not do well. Okay, this area where you have bias low and variance high is called as overfitting. What do we call this? Overfitting. Overfitting is, okay, mugging up by hearting the class problems, doing well in the class, but not doing well in the exam. Okay, test is also called validation, isn't it? So test error is also called as validation error. So this is your test error or validation error. Validation error or test error. Okay, where you are actually mugging up all the answers and you are doing well here, not doing so. This is called area of overfitting. Okay, this is the best. This is what we actually want to achieve. Okay, the reason why we evaluate, and we should evaluate both training and test always and see the value. If they are somewhere here, we accept that performance of the model. We say model is performing best here. Okay, this is called area of underfitting. Underfitting. Underfitting is easy to remember. Both is doing bad. Okay, you can improve. There's scope for improvement. That means you have not been trained enough. Okay, that's not your mistake. It is mistake of faculty. You know, they have not trained you enough. So you do not have enough data. Okay, or you have not fine-tuned you have not tuned the parameters properly. And we'll talk about those things. Okay, so tomorrow itself we'll talk about it. Okay, so when you have scope for improvement, it's called underfitting. And how do you know? You can know if the errors are high or accuracy is low in both the cases. As you keep on adding more and more, as you keep on adding more data, both of them will decrease. After a certain point, test will start increasing. So that point where test is start increasing, you know that you are now getting into overfitting zone. You're getting into overfitting zone. Okay, so you should, if you are here, you should come down. But once you are here, you should not go up. Okay, so we will learn how to find this spot. Okay, and this is the best value which model can give you. This is considered as the best result of this model. And when we run 10 models, for each of the 10 model, you find this, and the one that gives you best result here is the best model. Any questions so far? Okay,
No.
so with that, we stop our discussion today. Tomorrow, we'll start with multiple linear regression, and we will test all these things that we have discussed today. Make sense?
Yes.